Good afternoon, everyone. So, welcome you all for the second session for the problem solving session of the NPTEL course Fluidization, Computational Fluid Dynamics. So, we'll wait for 2 more minutes for others to join and we'll start by 3 4 or 3 5. Okay, we'll start the session now. Let others join in the meantime. So, let me introduce myself. I am Kartiga. I am a research scholar from IIT Hyderabad. So, I am basically working on the modeling on CFD and DEM based modeling on mineral processing applications. So I'll be handling the problem solving sessions. So in these sessions, as we discussed in our last class itself, we will be solving problems related to that week's assignments so that it will be useful for you in submitting the assignments. So this is week 2 and the course, as you all know, is Computational Fluid Dynamics and course code is given over here. So every week the session happens from 3 to 5 p.m. 2 hour session, and it is being held every week. It will be held on Saturday afternoon. So as you all know, the course instructor is Professor Sreenivas Jayanti sir from Department of Chemical Engineering, IIT Madras, and myself, a research scholar from Chemical Engineering Department from IIT. So I welcome you all to the second session for the CFD problem solving session. So by now, actually, I hope you got an idea of what computational fluid dynamics course will offer you and what you will get at the end, and what should be like you be doing along the course so that you can get a better understanding. Oh, sorry. So it is, since it is a 12 weeks course, we are going from basics to in-depth understanding of the concepts in CFD. So in the first week itself, I hope you all had seen the lecture videos from the professor. So the course lectures will be available from the NPTEL site through their videos, and while we will be dealing with the problems related to that week's assignments. So in the first week, that is, we have seen about the calculation of flow through a rectangular duct, and in week 2 we are going to deal with problems about fully developed flow in a triangular duct, and later we'll be seeing about derivation of equations governing fluid flow, and mainly about incompressible flow equations and what are all the boundary conditions that normally we associate with. And later it is about basic concepts of CFD through finite difference approximations, and basic concepts of CFD like consistency, stability, convergence, and solution of Navier-Stokes equations for compressible flows. And it is about incompressible flow solutions using Navier-Stokes equations. And also, like, at last it will be about mathematical concepts of linear algebraic methods, basic getting solution for the linear algebraic methods through basic methods and as well as advanced methods. And last it will be finite volume approach including grid generation and turbulence flows and turbulence modelings. So basically what CFD is, what our understanding is from the last class is that CFD is nothing but we are getting the solution of the fluid flow in a system by means of solving the equations. And those equations are nothing but if it is a simple flow, that is only water or any fluid alone is flowing, we'll be having to deal with only two equations. One is continuity equations, the other one is Navier-Stokes equations or the momentum conservation equation. And if at all we have other aspects in the flow system, for example, in generalized cases, in when we are dealing with the chemical production companies, I mean production industries, there won't be no always cold flow, right? There will be like heat transfer and there will be reaction happening inside the system as well, and there can be separation by means of electrochemistry also happening. So if at all these things are happening, we need to introduce additional equations as well, like heat exchange energy exchange equations and energy equations and reactions. If it is occurring, we need to introduce the kinetics of those equations as well. But in generalized case, for you to get a basic understanding of the CFD, you need to have a clear understanding of continuity equations and Navier-Stokes equations. That will give help you like go through the basics. And later when you move on to different applications, turbulence, all those things will come into picture and the model complexity will increase. But in the beginning, it is sufficient to understand basic things. So we have equations governing the flow inside the system, the continuity equation and Navier-Stokes equations. So is it possible to get analytically the solution for that particular flow? For example, if pipe flow is happening, we can get some analytical solution. But if it is a complex system, we cannot always obtain the analytical solution. So what we do is we discretize the system. We divide the system into smaller segments and we solve equations, the same equation across all the particular grids, so that we will get the solution at all those grids, and the information will be passed from one grid to other. Like for example, if if this is the grid system under our consideration, for the ease of solving we will be dividing the system into smaller segments using meshing, so that we can solve the equation in each grids and the information will be transferred across the grids. Like equations will be solved here and it will be transferred over here, like that we will be passing the information. And also we know the value at the boundaries, like this if it is a flow through pipe, one end will be inlet and in the inlet only we will be passing the fluid, so we know the inlet velocity. And the outlet, like the where it opens, it can be like pressure outlet, oh, pressure outlet, so those things can be there. And so inlet and outlet condition we know, and walls also we give no slip conditions, that is velocity at the walls will be zero. So these are few conditions we will give for us to help in solving the equations. So first what we are doing, we are just we need to know what system we are dealing with. Whenever we are approaching any CFD problem, we need to know what system we are dealing with, and that particular geometry we need, and that particular geometry we use this meshing, and we divide it into smaller segments. So for example, initialization, if we say, we need to know the geometry and we are meshing that geometry. These things we do in pre-processing, and after meshing we are giving the initial condition and boundary condition. Like at time t is equal to 0, we know the temperature of the system is this, and if we are heating that system, we can say like the heating rate is this, and after some time, so based on the heating rate we can calculate, and initial temperature we know. So step by step increment if it is occurring, we can say that after time t equal to 5 seconds or something, we can say the temperature has risen to this. So for that we are giving initial condition and boundary condition. Boundary condition is nothing but like along the boundaries of the system, we should know what condition it is being maintained. As I mentioned, inlet we have velocity as this, and in the outlet it is open to atmosphere, and the surroundings rest all is covered with wall. So we are using no slip boundary conditions. So those type of things we are giving, and after giving initial condition and boundary condition, we are using solvers and getting the solution for that. Like we are solving these Navier-Stokes equations and getting the values of fluid motion if it is occurring, and also we know the position of the fluid in the next cells, and also we know values like velocity, temperature if we are dealing, all those things we will get. And after getting all those values, we will just analyze the thing and we'll say whether it is right or wrong. See, most of the time, actually, I remember a professor of mine once told like CFD will not always give the right solution at the first moment itself. Like it will give solutions and it should be meaningful. For us to get meaningful results, we need to define everything rightly, and also the solvers should also be rightly, appropriately chosen. Like it is in our hands and we should choose it wisely, because if like at last we will be post processing the results and we will be getting a colorful images, actually like velocity contours. If we are saying velocity is high at one point, velocity is low at one point, those contours we will be using to visualize the results and present this data. So if we are not focusing on utilizing the correct approach, we will be at last left with colorful diagrams, but not the correct ones. So it is, so we should be like getting a proper things like geometry, meshing, everything is important, but solution, so everything is important. That is what here it is, equations governing fluid flow. We are dealing with what equations we require in this sense in dealing with the CFD, and like then we go with the finite difference approximations, wherein we actually convert the partial differential equations. So those equations that are available are in the form of partial differential equations, and we need to convert it into the algebraic form for us to get the solutions. So, and there are a few criteria like solution we should be obtaining in a stable, and solutions should be converging, consistent results should be there. So those are all few criteria which you will be dealing with as the course progresses, and later we deal with solutions, and this is numerical methods which we use to get solve the system of equations, and it can be basic methods or advanced methods. And later it is about finite volume approach. So basically there are three main things: finite difference approach, finite volume approach, and finite element approach. So finite difference is wherein you are easily dividing the system, and in the form of x plus delta x, So in those things, and finite volume, like a volume, I hope in the triangular duct problem, finite volume approach you would have seen. And last one is finite element. Mostly chemical engineers, in I'm talking about most of the cases, it is not being that used. Mostly civil engineers, those people will be using, as far as I have seen. So not, I'm not generalizing it, but my in my knowledge. So coming to the books and references, uh, this is Computational Methods for Fluid Dynamics and by Ferziger, and Numerical Computation of Internal and External Flows by Hirst, and Patankar, Numerical Heat Transfer and Fluid Flow, and Verstig, Malal Sekara, and Introduction to Computational Fluid Dynamics Finite Volume Method. Anderson, Computational Fluid Dynamics Basics with Applications. So for going to understand the basics from the scratch, Anderson would be helpful. I don't know for what purpose you all have chosen this course, like whether it is for your project or your for a job or something. CFD is actually very useful course because it will be up. It has variety of applications to deal with, and it does not have limitations on its scope. Like you can apply it to any system and so on. Like it is widely used. So now coming back, we are into week 2. So that's why I gave a very large introduction, because some people might not be aware of why we are doing these things in CFD and what we are doing. That for getting that awareness only I gave those small things. So coming to week 2, mostly this week's problem focus on flow through triangular duct. So in week 1 it was mostly about flow through a rectangular duct, and in week 2 mainly it is about flow through triangular duct. So for flow through triangular duct, we use the finite volume approach, and let us see what all problems can be asked, like and what things you need to focus on. Those things we'll see now. So first we'll see the practice problems, and later we'll move on to some sample problems. The first problem is actually based on a case. So just focus on, there are two figures, figure 1 and figure 2. So what exactly you are getting, just think for a moment, and we will see, like the problems coming in the next few slides are actually based on this particular figure. So just take a minute and see what the figure is about. You can make some inferences from this figure actually, so just check to that. And at any point, if you have any questions, you can actually unmute yourself and ask. You need not wait for the till the last session, because I might not check if there is any message in between. And if there is any feedback also, you can say. Okay, we'll now start with the session. So the first figure is actually through a triangular duct. So here it is a YZ plane. The plane that we are given is a YZ plane. So we can assume that the flow is taking place through the X, like the other thing will be X. So flow is taking place in the X direction, and this is a ZY plane. So we have discretized the system, divided the system into 16 triangles, and the equations that we are solving will be on these triangles only. And this is figure 2. Here we have somewhat ellipsoid channel. Again here it is in the xy plane. So the flow will be in the z plane, z direction, not z plane. Flow will be in the z direction. I mean, direction can be varying. Again here it can be, I'm not sure of the x direction, it can be this way or that way. But You get my point, right? The flow is in x direction in the figure 1, and while the flow is in z direction in the figure 2. So that is the important takeaway. And in figure 1, it is the flow domain is divided into 16 triangles. So the questions can be asked in any form from these from the figures. So first we'll see that with respect to figure 1, for the given coordinate system, the governing equation describing steady laminar flow through the triangular duct is given by dash. So with respect to the figure 1, for the given coordinate system, the governing equation describing steady laminar flow through triangular duct is given by dash. So now the first problem is about flow through the triangular duct, and it is mentioned that the flow is a steady state flow and it is a laminar flow, and we are asked to find the governing equation form. Okay, so we'll first look at the options. First one, option A, it is mu into dou square u by dou x square plus dou square u by dou y square equal to minus dou p by dou z. And option B, it is mu into dou square w by dou x square plus dou square w by dou y square equal to minus dou p by dou x. Option C, mu into dou square u by dou y square plus dou square u by dou z square is equal to minus dou p by dou x. And option D, it is mu into dou square v by dou y square plus dou square w by dou z square is equal to minus dou p by dou x. So now actually from this itself you can say the answer. So anyone wants to try giving the answer? Okay. Okay, answer is actually C. I'll tell you why. But anyway, thanks for the answer. So when we look at figure 1, we'll go back to figure 1. So this is figure 1. So this figure is in ZY plane. So the flow is occurring in x direction. So we have x velocity, that is u is component, x component velocity is there, and that x component velocity is a function of y and z. So that therefore, and pressure gradient will obviously be in the x direction. So on that basis actually we can rule out option A, and option B, it is again we are having it is a mix of equations, so we do not have w component velocity actually, so option B is false. Whereas option C, it is it here u component velocity is there and it is a function of y and z. So this both the terms would be remaining, and dou p by dou x is also there. Again, when we come to last, like v component and w component velocity won't be there. So what we need to be, even though the variation is in y and z direction, that aspect is right, but we have, when we take we three components of velocity u, v and w, u is x component velocity, v is y component velocity, w is z component velocity. So u is actually a function of y and z, and v and w are actually 0. So maybe that component part might have been confusing for everyone, but like v and w are components of velocity in the y and z direction. So therefore they are 0 actually. So answer is therefore option C. So mm, sorry. So we are mentioned, it is mentioned in the problem that it is a steady laminar fully developed flow through the triangular duct. So the flow is occurring through the duct. So it would be like this, duct will be extending. So it is in the wide x direction. So flow is in the x direction. So u component velocity remains, and that u component velocity is a function of y and z directions. I mean that u component velocity is varying in the y and z direction. And so now we are writing continuity equation. So continuity equation is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Again, this is satisfying. Continuity equation is satisfying because v and w are 0, and again u component velocity is not varying with respect to x. So if we make v and w 0, right, dou u by dou x is equal to 0. So u is not varying in the x direction. So continuity equation is satisfied. Next we are dealing with the momentum equation or the Navier-Stokes equation. So we have three components: x component, y component, and z component. So for the first component, that is x component, we have rho into dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z equal to minus dou p by dou x plus rho gx plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. And similarly we have y component and z component equations, but in this particular thing we are not considering the equations, but for general purpose we will see how the equations are varying. So first it is rho into, where is my, rho into dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z equal to minus dou p by dou y plus rho gy plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. And similarly this is x component and this is y component and this is z component. So rho into dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus dou p by dou z plus rho gz plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So these are the three components of velocity, components of the equations, that is Navier-Stokes equations. So for in general, for the cold flow system, cold flow in the sense there is no any external energy transfer inside the system. So in those cases, these are the four equations that we will be solving. First one is the continuity equation, and second one is the x component momentum transfer, y component momentum transfer, and z component momentum transfer. So three momentum transfer equations and one continuity equations we will be solving to obtain any solutions. So now coming back to our system of interest, we have a triangular duct flow and it is mentioned steady flow, laminar flow and fully developed flow. So here flow is in the x direction, like flow is in this direction, and therefore only x component velocity remains, and that x component velocity is a function of y and z that we can obtain from continuity equation as well, because v and w becomes 0, dou u by dou x is equal to 0, and so u is not varying in the x direction. So now momentum equation we have. So we'll take this. So only the first equation remains, right? Again, it is a steady state, so u is not varying with respect to time, and u into dou u by dou x. So dou u by dou x is 0 because u is not varying with respect to x. So dou u by dou x is 0, and here v becomes 0 and w becomes 0, and the whole term in the left hand side becomes 0. Coming here, we are not considering the body force in this particular system. So rho gx we are not including, and we are left with pressure gradient force and viscous force. Pressure gradient force is there and viscous force is there. So dou P by dou X is there, and in this viscous forces we have mu into, that is viscous stresses, mu into dou square U by dou X square plus dou square U by dou Y square plus dou square U by dou Z square. So U is a function of Y and Z, so the first term becomes 0. So we are actually putting LHS equal to, and we have minus dou P by dou X plus mu into dou square U by dou X square plus dou square U by dou Y square plus dou square U by dou Z square. And we are just taking the terms to the other side. Dou square U by dou Y square plus dou square U by dou Z square is equal to minus dou P by dou X. Sorry. Mu into dou square U by dou Y square plus dou square U by dou Z square is equal to minus dP by dx. So that is how we are obtaining equation. So mu into dou square U by dou Y square plus dou square U by dou Z square equal to minus dou P by dou X. So the main takeaway is that flow is happening in the x direction, and because of that we have our x component velocity u. Component velocity, and because of that x component velocity, and that x component velocity is a function of y and z. That is how we are obtaining this equation. You can either derive the equation, or best way would be to eliminate options. So on eliminating options we can get the solution. So this is question 1. Now let us move on to question 2. In question 2, it is asked that steady fully developed, once again I'll just change my cursor. Yeah, steady fully developed flow through the duct shown in figure 1 represents a balance between which of the following terms. So figure 1, that is the flow we saw in the last slide, flow through a triangular duct. Similarly, it was steady flow, fully developed flow through the triangular duct, wherein the flow was in the x direction, and we have x as a function of y and z. I mean x component velocity as a function of y and z. That we have seen. Now let us see what this particular question is asking. So steady fully developed flow through the duct shown in figure 1 represents a balance between which of the following terms. So we'll see the question. It is asking about balance between which of the following terms. So first one, it is inertial. Second one, viscous force. Third one, pressure force. So the question we have seen, I mean the flow also we have seen, the flow is nothing but flow through a triangular duct. So in that flow through the triangular duct, what are all the balance we are able to see in the figure 1. It represents a balance between which of the following terms. First one, inertial force. Second one, viscous force. And third one, pressure force. So we'll see the options first. Option A, 1 and 2. Option B, 2 and 3. Option C, 1 and 3. Option D, 1, 2 and 3. So the answer to this question is nothing new. It is from the previous question, from the answer only. Like in the previous question, we have solved the equations and got the final equation to be solved. I mean, we have simplified the equation and got the final equation that. So answer to this particular question is again from that question only. So it is viscous force and pressure force. So option B, that is 2 and 3 is the right answer. Steady fully developed flow through the triangular duct shown in figure 1 represents a balance between which of the following terms. So it is viscous forces and pressure forces. Yeah, option B. Option B is the right answer, correct one. As you have correctly pointed out, option B is the correct answer. It is a balance between viscous force and the pressure force. We can once go and check the equation also. It is mu into dou square u by dou y square plus dou square u by dou z square is equal to minus dou p by dou x. So it is a balance between pressure force and viscous forces. So option B is the right answer, like you have mentioned correctly, and it is a balance between 2 and 3 viscous forces and pressure forces. So the correct answer is option B. Now let us go to question 3. In question 3, what is asked? The vector form of the governing equation for flow through ellipsoidal duct shown in figure 2 is dash. The vector form of the governing equation for flow through the ellipsoidal duct shown in figure 2 is dash. So now here actually there is one small thing you need to be careful in the question. The question is not about governing equation. It is about the vector form of the governing equation for flow through the ellipsoidal duct. So we'll see the options first. So option A, it is mu into del dot del u equal to minus dp by dx, and option B, it is mu into del dot del v equal to minus dp by dy, and option C, it is mu into del dot del w is equal to minus dp by dz, and option D, it is mu into del square u equal to minus delta p. So actually here in the last option u is nothing but u is the velocity vector. So the question is also about vector form of the governing equation for flow through ellipsoidal duct shown in figure 2. In figure 2 actually ellipsoidal duct flow was shown and the flow was in z direction. But in this particular question it is not asked about the governing equation, but rather the question is about vector form of the governing equation. So we need to give a generalized equation, generalized Navier-Stokes equation in the vector form. We need not go in the component form of the Navier-Stokes equation. So option A, B and C, if you look at it clearly, those are all component wise equations. Dou p by dou x, dou p by dou y, dou p by dou z are all x component, y component, z component Navier-Stokes equations. Whereas the option D, that is last option, mu into del square u equal to minus delta p, where u is the velocity vector. So option D is the right answer. Answer is option D. So if we look at what to say, vector form of the equation, the continuity equation will look something like this. Del dot u is equal to 0, whereas it would be, if you put it in using the each components, it would be dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. But vector form, it is del dot u equal to 0, and u here is the velocity vector, remember that. And for momentum equation, we are writing the equation as rho into dou u by dou t plus u dot del into u equal to minus delta p plus rho g plus u into del dot del u. So momentum equation or the Navier-Stokes equation in the vector form looks something like this, and it is a steady flow, laminar flow. So on that basis we are actually cancelling out the LHS terms, and also here we are not considering the body force. So it is minus delta p plus mu into del dot del u equal to 0, and p is the pressure gradient force and mu is the viscosity and u is the vector component of the velocity. So that is how we are obtaining the equation. So careful, where we need to be careful is that we need to be very careful while reading the question. It is not asked the governing equation for flow through triangular duct. Rather, the question is vector form of the governing equation. So here mu into del square u equal to minus delta p, and u is the velocity vector and p is again the pressure gradient. So answer is option D. And coming back to question 4, which method would you use to solve for the velocity field in the ellipsoidal duct if you wish to solve in the xy coordinate system? Which method would you use to solve for the velocity field in the ellipsoidal duct if you wish to solve in the xy coordinate system? So options are finite volume approach, and second one is finite difference method, and third one is finite element method. So we'll look at the options once. Option is 1 only, option B it is only 2, and option C it is 1 and 3, and option D it is 2 and 3. So answer actually is option C. Okay, like here actually it is difficult to go for the finite difference approach when we need to solve in the xy coordinate system, because we cannot since it is an ellipsoidal duct, we cannot put it in the xy coordinate system. Like here mostly in finite difference how we use is x plus delta x, xy plus delta y, so those type of things we give. But in finite difference approach, as I mentioned, x plus delta x and y plus delta y, those type of definitions we cannot give in the finite difference approach when we are using the xy coordinate system. So like ellipse we cannot define it that way, right? So better approach would be going with finite volume approach or finite element approach. Finite volume we can divide the system in any means and solve the equations, and similar thing is the finite element approach. In finite element approach, like it will be like small elements will be taken and it will be solved. So answer is option C. Now we'll go to question 5, and this is the last problem for the practice problems, and from next on we'll see the sample problems. So for the domain shown in figure 1, if wall velocity is specified to be 0, how many equations would need to be solved? So this is the flow through the triangular duct, and if we are specifying the wall velocity as 0, how many algebraic equations do we need to solve? So options are option A 6, option B 7, option C 13, option D 16. So we have four options. Option A it is 6, option B it is 7, option C 13, option D 16. So now if we look at the domain, we have a triangular duct problem, and we have divided the domain, or we have divided the triangular duct in the xzy plane into 16 triangles, and it is mentioned that wall velocity is specified to be 0. That is, the velocity along the wall is specified as 0. This is what we call as no slip boundary condition. And now how many equations do we need to solve? uh, so what would be your guess? Okay, actually the answer is option D. That is 16 is the answer, because for each of the domain we will be getting one equations, and in that equation, since we are using finite volume approach. So if we are using finite volume approach, for each of the triangle we will, that is I am talking about the small triangles. For each of these triangles we will be writing equations, and all those equations need to be solved. So 16 triangles are there, and we need to solve 16 equations. And in those equations, some components or some coefficients will be 0, because because of the no slip boundary condition. That is, wall velocity is specified to be 0, so those terms may cancel out. But apart from that, we have 16 equations we need to solve, and we'll be having 16 unknowns as well. So for the domain shown in figure 1, if the wall velocity is specified to be 0, how many algebraic equations would need to be solved? So the answer is option D, that is 16 is the answer. Now we'll go to questions, sample problems. So the first problem is that okay, again here we are having one case with three problems, like three figures, more than problems, I would say three figures. So all the coming problems are based on these figures only. So the first, what is the difference we are seeing is that mostly the flow is in the xy direction, and in figure 1, 2 and 3 the division is different actually. The gradient, the finite volume approach, we use the triangles, and what to say, the squares as well. So the way of discretizing, that is dividing the system, is different in figure 1, 2 and 3. So that is the difference. Like here it is a generalized system, and here we have discretized in one means, and here we have discretized in other means. Here it is a combination of square and triangle cells, whereas here we are having all triangle cells. So we'll see what the problems are. Mostly the problems coming up are based on these figures only. So just observe, and based on the axis given, we are able to see that the flow is in the z direction, because we are given xy plane. Mostly the flow is in the z direction. So now we'll start with the problem. Okay. Questions for the following problems have reference to the following three figures. Questions for the following problems have reference to the following three figures. That is what I have mentioned. And choose the correct answers from the options given below. So from these three figures, we need to identify the correct options. From these three figures, we need to apply all the questions and get the correct options from the options given over there. And following notations is to be used wherever applicable. U, that is the velocity vector, and U, V, W are velocity components in the XYZ direction. P is the pressure, mu is the viscosity, Nx and Ny are direction cosines. So I hope it is clear. Whatever the questions that are coming up, we have around 14 problems, and all those problems are actually based on these three figures, and we have these for notation or the symbols wherever we are using. So we need to be conscious of the meanings. So U is the velocity vector, and UVW are the velocity components, and P is the pressure, mu is the viscosity, and Nx and Ny are direction cosines. So we are clear now, right? We will now proceed with the problems. Okay. Question 1. You wish to compute the steady laminar fully developed flow field through the triangular duct shown in figure 1. For this case, the governing equation is given by dash. I read the question again. You wish to compute the steady laminar fully developed flow through the triangular duct shown in figure 1. For this case, the governing equation is given by dash. I'll read out the options. Not options, it is few statements are given. First one, it is del dot del w equal to 0, and second one, del dot del u equal to constant, and third one, it is del dot del u equal to minus mu delta p. So these are the three representations given. First one is del dot del w equal to 0, and second one is del dot del u equal to constant, and third one is del dot del u equal to minus mu into delta p. And now we have to choose from the options given below. First one, it is 1 only, second one it is 2 only, third one it is 3 only, option D it is none of the above. So I'll read out the question again. We are computing for the triangular duct. If we remember the triangular duct, it is a simple triangular duct, and I guess it is in the xy plane, and therefore I guess the flow is in the z direction. So it is a steady laminar fully developed flow through the triangular duct. For this case, the governing equation is given by dash. First one, it is del dot del w equal to 0. Second one, del dot del u equal to constant. And third one, del dot del u equal to minus mu into delta p. So which of the following three are right, or all three are wrong? So that is given in the options. So what do you think is the answer? Okay, answer is option D, that is none of the above is the answer. I'll tell you why. Answer is option D, none of the above. So this is flow through triangular duct, and it is in the xy direction, so flow is in the z direction. So steady fully developed laminar fully developed flow through the triangular duct, and since it is in the xy plane, flow is in the z direction. So therefore w component velocity remains w equal to w is a function of x and y. So continuity equation, it is dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. And momentum equation, again we have three equations. First one is the x component momentum conservation equation, that is rho into dou u by dou t plus u into dou u by dou x plus v into dou u by dou I plus w into dou u by dou z equal to minus dou p by dou x plus rho gx plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. And second one, it is rho into dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z equal to minus dou p by dou y plus rho gy plus mu into dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. And the last one, it is rho into dou w by dou t plus u into dou w by dou x plus v into dou w by dou y plus w into dou w by dou z equal to minus dou p by dou z plus rho gz plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So these are the three momentum conservation equations in the x, y and z components, in terms of x, y and z components. So we have four equations as we all mentioned. So now we need to solve the equations and we need to simplify it basically. So it is a fully developed flow through the triangular duct, and therefore w velocity remains because flow is in the z direction, and w is a function of x and y. So first we go to third equation, and it is a steady flow equation. So this term becomes 0, first term becomes 0, and u component is 0, v component is 0, w component, although it remains, it is not varying with respect to z. So this term also becomes 0. And we are left with minus dou p by dou z plus rho gz and plus mu into dou square w by dou x square plus dou square w by dou y square plus dou square w by dou z square. So we have only this term, and this is 0 because w is not varying with respect to z. So simplifying, we write it as 0 equal to minus dou p by dou z plus mu into dou square w by dou x square plus dou square w by dou y square, and this term actually becomes 0. It becomes 0 in the next one. Dou square w by dou x square plus dou square w by dou y square equal to minus dou p by dou z 1 by mu. and that is the equation which is the simplified equation in with regards to our context of the question. So now what is the answer? Why is it none of the above? The equation for steady fully developed flow through a triangular duct is therefore del dot del W equal to constant. So it is del dot del W equal to constant because pressure gradient can be constant. And so going back to options, del dot del W is not zero, it is constant. Actually the pressure gradient, it can be constant, but it is not zero. So option 1 is false. And second one, even though it is given del dot del U equal to constant, but it is not U component of the velocity, it is W component of the velocity. Unless until mentioned as a vector form, don't consider U as the vector. So here it is the component, and there it was again bold written for the vector. Vector mostly it will be written in bold, or it will be written with that overhead arrow. So that is, so coming to the options, first one, the answer is del dot del W equal to pressure gradient, and it can be del dot del W equal to constant. So it can be constant, but it is not zero, so therefore option 1 is false. And second option, it is del dot del W is constant, not del dot del U is not constant. So second one is also false. And third one is again different components, del dot del U. If it is del dot del W, we can consider, but it is not, and therefore it is wrong. So answer is none of the above is the right answer. So option 1 is wrong because it was given del dot del W as 0, but in the what we obtained is del dot del W equal to constant, so it is option 1 is false. Option 2 has wrong velocity component, it was mentioned as U, again it is wrong. And third one is also dimensionally incorrect, that also has wrong velocity component, and apart from that it was mu into dou p, it is delta p divided by mu, it is not mu into delta p, so that is also false. But we can actually consider it as, if we consider it as a vector form, but dimensionally it is wrong. So I hope it is clear. Okay, 16.3. Okay. Okay, I'll keep sound high because I didn't hear the last few things. Okay. Okay, we'll see. I hope it is clear now. We'll see question 2. In question 2, again it is, you wish to compute the steady laminar fully developed flow field through the triangular duct shown in figure 1. For this case, which of the following is an admissible governing equation? You wish to compute the steady laminar fully developed flow through the triangular duct, and for this case, which of the following is the admissible governing equation? So coming back, first one, it is dou square W by dou x square plus dou square W by dou y square equal to 10. And second, it is dou square U by dou x square plus dou square U by dou y square equal to 10. And third one, it is dou square W by dou x square plus dou square W by dou y square equal to minus 1 by mu dou p by dou x. And options are option A 1 only, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So which do you think is the right answer? You wish to compute the steady laminar fully developed flow field through the triangular duct as shown in figure 1. For this case, which of the following is a admissible governing equation? So this is same equation that we derived in the last slide, but in the some with some numbers given. So which of the following is the right answer? So option 1, it is dou square w by dou x square plus dou square w by dou y square equal to 10. Or option B, 1 and 2. 2 is dou square u by dou x square plus dou square u by dou y square equal to 10. And third, it is dou square w by dou x square plus dou square w by dou y square equal to minus 1 by mu dou p by dou x. Or in the option D, it is all three are right. So which do you think is the right answer? Answer is actually, did anyone answer? A is the answer. Option A is the answer actually. Because see, what issue is that uh, the pressure gradient can be constant actually. Minus mu 1 by mu dou p by dou z. If in the equation, when we are deriving the equation, when we are simplifying the equation, it is dou square w by dou x square plus dou square w by dou y square equal to minus 1 by mu dou p by dou z. So because of that, third is wrong actually. So answer is option A is the right answer, one only. So how? Because it is a steady flow, laminar flow, fully developed flow through the triangular duct, and in the equation it comes as the z direction the flow is there. So w component velocity is there, and that w component velocity is a function of x and y. So it is dou square w by dou x square plus dou square w by dou y square equal to minus 1 by mu dou p by dou z. Dou p by dou z can be constant, so it is equal to 10. So that is one admissible form. Second one, it is u component velocity is not there, so it is not true. Third one, it is the RHS side, it is mentioned as dou p by dou x. So but the answer is dou p by dou z. So therefore third statement is wrong. Because of that, right option is option A. One only is the right answer. So now we will see option A, one only. For fully developed flow, the pressure gradient is constant. Option 1 is suitable. Option 2 has the wrong velocity component, as we saw it is u, and option 3 has a wrong pressure gradient. So option 3 is also wrong. So because of that, in the option wise it is A, that is one only is the right answer. Now we will again look at question 3. Okay, let us just take a 2 minutes break or 3 minutes break. We'll start with question 3 by 4:08. Time now is 4:05. So we will start by 4:08 sharp. Just a 2 minutes break. Okay. Hmm. Yeah, we'll start now. Start now. Question 3, it is about which of the following boundary conditions is applicable on the diagonal segment of the boundary shown in figure 1. So which of the following boundary condition is applicable on this particular boundary? So option A, P equal to constant. Option B, nx into dou w by dou x plus ny into dou w by dou y equal to 0. And option C, it is w equal to 0. And option D, it is boundary condition is not needed. So the question is about asking which of the boundary conditions can be applicable on the diagonal segment of the boundary shown in figure 1. So this is the diagonal segment, and which of the boundary condition is applicable. So we can consider, if we are considering the flow through the triangular duct, we can say it as the wall boundary condition. And mostly in wall boundary condition, what we give is that since it is a stationary wall, we consider the velocity as 0. W equal to 0 gives the appropriate boundary condition for the flow. So which of the following boundary condition is applicable on the diagonal segment of the boundary? So it is the no slip boundary condition. So no slip is nothing but the velocity is 0 and W equal to 0. So it is velocity of the fluid equal to the velocity of the solid, and solid nothing but wall. So if wall is not moving, it becomes 0. So that is the concept, and therefore option C is the right answer. So since what we do in CFD is that when we need to get the, we are using the no slip boundary condition or something, we just refine the mesh near the walls to a very finer mesh, so that we can get exactly the right value, to appropriately get the true value near the boundaries. We mostly fine tune the mesh. That is, I showed we are dividing the system into smaller grids, right? Those grids will be very much finer near the walls in most of the problems. Why? Because we use the no slip boundary condition or something, we need to get finer and appropriate values. So in those segments, we use that. That is just for your information, not related to this problem. What is related to this particular problem is that what is the boundary condition that is applicable, and here it is no slip boundary condition can be used, and it is W equal to 0. So option C is the right answer. Answer is option C, that is W equal to 0. And no slip boundary condition W equal to 0 is applicable on all the boundary walls, not only on this wall. It is applicable on all the boundary walls. Option B implies 0 shear, which is not correct. So dou W by dou X, okay, dou W by dou X plus dou W by dou Y, if it is 0, it implies 0 shear, and which if you put it in the Navier-Stokes equation, like those terms in equate to shear stress, right? And that shear stress, if it is 0 only, this particular equation can be used. So just a substitution back in the Navier-Stokes equation gives form as shear stress is equal to 0, which is not true. So 0 shear, therefore option B is false. Hope you got it. Now we will move to question 4. In question 4, what is asked? For steady, laminar, fully developed flow field through the triangular duct shown in figure 1, which of the following equations are is or are applicable? Again, steady, laminar, fully developed flow through the triangular duct shown in figure 1, again the same figure. Which of the following equations are applicable? First one, it is delta P equal to constant. Second one, del dot U equal to 0. Third one, del dot delta P equal to constant. And option A, 1 only. Option B, 1 and 2. Option C, 1 and 3. Option D, 1, 2 and 3. So I'll give you one clue. Here U actually it represents a vector form of the equations. So U is not x component velocity, it is a generalized vector form. So which of the following is applicable? Or else like component form, yeah. So which of the following is applicable for a steady fully developed flow through the triangular duct shown in figure 1? Which of the following equations are applicable? So we have got three equations. First one is delta P equal to constant, and second one is del dot U equal to 0, and third one is del dot delta P equal to constant. So four options are given. First one it is 1 only. Second one it is 1 and 2. Option C it is 1 and 3. Last one it is 1, 2 and 3. So which of the following is correctly suiting the system, that is steady laminar fully developed flow through the triangular duct, and which of the equations are applicable? So any answers from your side? Answer is actually B as well, because as I mentioned it is like a vector form, so it is del dot U equal to 0, that is a continuity equation, right? So del dot U equal to 0, and first statement, that is delta P is equal to constant, is also true. Delta P is equal to constant and del dot U equal to 0. Third one, del dot delta P equal to constant, it is false, because delta P is constant means del dot delta P would be 0, it won't be constant. So option uh, B is the right answer, 1 and 2. So option B, 1 and 2 is the right answer. For incompressible flow with constant properties, option 2 is correct. Like for incompressible flow with constant properties, del dot U equal to 0. And fully developed flow, option 1 is correct. And option 3 is correct only if that constant is 0. So del dot delta P equal to constant was option 3. But del dot delta P equal to 0 is the thing. So if constant is 0, that is correct. But it was not given as 0. So option 3 is wrong. So only option 1 and 2 are right. So option B is the right answer. Now we'll go to question 5. Now from question 5 we are going with figure 2. So figure 2, previously we have just dealt with figure 1. So in this particular question, let us see what has been asked. So we'll read the question. You wish to find the velocity in the starred cell in figure 2. How many algebraic equations do you have to solve? So we are asked to find the velocity in the starred cell in figure 2. And how many algebraic equations do we need to solve? First one, option A, it is 1. Option B, it is 4. Option C, it is 6. Option D, it is 10. So what is asked? We are asked to find the velocity in that particular cell, starred cell, that is in figure 2. So this is figure 2 and we are asked to find the velocity in this particular cell. So how many algebraic equations do we need to solve? That is the question. So how many do you think we need to solve? I'll give you a clue actually. So the number of equations that we are solving has something to do with the number of cells in the figure, and that number of cells is same as the number of unknowns as well, and we will be solving all the equations simultaneously. Yeah, option D is the right answer. Option D is the right answer. Correct answer from your side. So option D, because we are asked to find the velocity in the starred cell, and we need to and it is asked how many algebraic equations we need to solve. So if we write equations, right, we will be writing uh, the equations for all the cells: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 cells are there. We write 10 algebraic equations and we will be getting 10 unknowns. So number of algebraic equations we need to solve is 10. Option D is the right answer. So we are using the finite volume approach in this particular thing. That is why we are getting that many equations and that many cells. So nx direction cosines, nx and ny outward normal for each side. So outward normal for each side is that, and gradients are evaluated at midpoints of each side using, I mean, these are all just concepts for the finite volume approach which we will be using. So I'll put everything out. So this is the this is how we write equation in the finite volume approach. That is integral over I n into del n dot del w dot dl equal to summation over j n dot del w over ji into lji equal to c into ai. So here it is expanding is nothing but nx, I mean integral or summation, it is nx into n dot del w, right, delta w. So nx into dou w by dou x plus ny into dou w by dou y over ab into lab. So it is like for each side we will be writing this side, this side, this side, this side. If we take this cell, we write components for this side, this side, this side, this side. And sometimes this velocity might be given, and those points we will be accounting later. But variation wise, if we see, it is nx into dou w by dou x plus ny into dou w by dou y over ab into lab plus nx into dou w by dou x plus ny into dou w by dou y into bc, I mean into lbc plus nx into dou w by dou x plus ny into dou w by dou y over the side ca into lca into c into abc. So this is I have given the expanded equation for the triangular portion. If it is a rectangular or square portion, we will be using a, b, c and d. So it is from, if it is AB, na, like from center point to the, how evaluation is made, that is what we are seeing. Nx and ny, I'll give you a better. So we are talking about this, right? So nx and ny are outward normal for each sides. So outward normal, those way we use nx and ny, and gradients are evaluated at midpoints of each side using values of the cell and those of the neighboring cells as the boundary conditions. So what is given over here? So as I mentioned, if it is about AB side, na, we will be using information from this cell and also from the below cell. So consider this is side AB. So for evaluating the gradient, that is dou w by dou x or dou w by dou y, we are evaluating it at the midpoint of the side using the values of this particular cell and those of the neighboring cells. So either with neighboring cells, or if it is this side, na, we have only information from this cell but neighbor cell information is not there, but again we have boundary conditions, so we use that. So that is how we use it in the finite volume approach. Finite volume approach, it is nothing but the product of nx into dou w by dou x plus ny into dou w by dou y over AB side into length of side AB. Similar way we use it for all sides and sum it up, and that will give area of that particular component and into some constant. So here we are using gradient and direction cosines in each equation. So how are we getting direction cosines are in the outward normal. So here it is outward normal. If it is like this, now we will be resolving it actually. Outward normal will be in this direction, and for that we will be getting nx and ny. Gradients are evaluated at midpoints of each cell using values of cell and those of the neighboring points. Gradients we will be evaluating at the midpoints of the sites by having the information from that particular side and that midpoint, or and that neighboring cell, or from the boundary condition information. So this is how we use the finite volume method. So based on this, for each cell we will have one equations, and the number of unknowns in the total equations will be equal to the number of equations, and we will solve them simultaneously. So that is how we do it. Figure 2 contains 10 cells resulting in 10 algebraic equations and 10 unknowns. So that is what here figure 2 contains. This is figure 2. Okay, this is figure 2. We have 1, 2, 3, 4, 5. This is 5, 6, 7, 8, 9, and this is 10. So we have 10 cells, so and 10 unknowns and 10 equations we need to solve. So answer is therefore option D is the right answer. Now we will go to question 5. Sorry, question 6. How many non-zero coefficients will be there in the discretized equation for the starred cell shown in figure 2? So how many non-zero coefficients will be there in the discretized equations for the starred cell in the figure 2? If we go back to figure 2, the starred cell is this cell, and there is no boundary conditions in the sides of this particular cell. So the number of unknowns will be like in x direction, two unknowns will be used, like this side one and that side one, and in above also y if we take 1 1, and for one variable for this we will include as well. So we have 5, I guess. How many non-zero coefficients will be there in the discretized equation for the starred cell shown in figure 2? So option A it is 4, option B it is 5, option C it is 7, option D it is 8. So answer is option B, that is 5 is the right answer. How? Because we have the starred cell, that particular cell is not surrounded by any boundaries. So if it is surrounded by any boundaries, that particular coefficient will become values or will become zeros depending on the boundary conditions that we are imposing. But here this particular cell is in the center and we do not have any boundaries, boundary conditions or any boundaries surrounding this cell. So in the x direction, along the x direction it will have one step forward and one step backward information. Similarly, in the y direction we have one step forward and one step backward information, and the information in that particular cell. So on the whole we have 5 non-zero coefficients will be there. So option B is option B is the answer. So now we will go to question 7. Okay, before that, yeah, this is figure 2, this is starred cell, and discretized equation in starred cell has Wij for second order will, this particular cell has, if it has Wij For second order, we will have variables wi minus 1 comma j and wi plus 1 comma j, as I mentioned, 2 in the x direction, and wij minus 1 and wij plus 1, 2 in the y direction and 1 in that particular cell. This is when we are using second order, and we will have 5 variables. So that is option B. Yeah, option B is the right answer. Now we will go to question 7. In question 7, it is asked that if the algebraic equations resulting from the discretization of the governing equation on the grid in figure 2 are arranged in the form of a matrix equation, then the number of rows having exactly 2 non-zero coefficient in the coefficient matrix is dash. So what is asked? So as we mentioned, like in figure 2, I guess, figure 2, we are just discretizing the equations, and we are obtaining 10 equations for 10 cells, and we are later arranging those governing equations that we obtained in the form of a matrix equations. So what is the number of rows that will have exactly 2 non-zero coefficients in the coefficient matrix? We'll look at the options. So option A, it is 0. Option B, it is 2. Option C, it is 3. Option D, it is 4. So here the question is about how many rows will have exactly 2 non-zero coefficients. So as I mentioned, we will have 10 equations. So each equation is like occupying one row. Consider it like that. And we have 10 unknowns. We know all the values at the boundaries. And in the previous question also, we have seen that the center cell has 5 non-zero coefficients. Imagine if the center cell has 5 non-zero coefficients, which of the cell will have 2 non-zero coefficient? You got my point? So center cell, which is surrounded by all, has 5 non-zero coefficients. So which cell will have 2 non-zero coefficients? The one cell that has more boundaries. So that cell should have boundary in the both the directions. So in that case, we will have 2 non-zero coefficients in the coefficient matrix. So answer is actually 2. 2 will be there because one in the topmost triangle and in the one in the bottommost right side triangle. In those two things, we will have 2 non-zero coefficients, exactly 2 non-zero coefficients. So answer is option B is the right answer. Option B, that is 2, is the right answer. We may obtain exactly 2 non-zero coefficients when the cell has only one non-wall boundary that it shares with a neighboring cell. So when a cell, okay, if a cell has only one side that it shares with another cell, if that is the case, remaining all the sides are surrounded by boundaries, we will have 2 non-zero coefficients. That is, I'll tell you. Okay, consider a triangle or consider a square also. We have, like in previous case, we have 1 in the x direction, 1 in the y direction. I mean 2 in the x direction, 2 in the y direction. That is 1 in forward and 1 in backward. 1 in forward, 1 in backward. This is x direction. So I minus 1. Okay. And this is j plus 1. And this is j minus 1. And this is I plus 1. Apologies for the worst writing actually, but still. I hope it is clear to you. If that is the case, it is fine. Okay, we have four sides, and if that four sides, it is actually sharing with the neighbor cells. That no, those neighbor cells are not boundaries. So in that case, what will happen? It four coefficients will be non-negative, and we will have one coefficient specific to this particular cell. So again that will add to 1. So 4 plus 1 we will have 5 non-zero coefficients. So that is what we saw in the previous question. That is the starred cell has 5 non-zero coefficients. Now when will it be 2 non-zero coefficients? That particular cell itself will have 1 non-zero coefficients, and it should have only one more non-zero coefficients that will come from the neighbor cell. So only one side it should be open to the other cell. It can be in the x direction. It can either, I mean, it can be like these three are no walls and this is open to a neighbor cell, or these three are walls and this is open to neighbor cells, or if in this case two are walls and it is open to neighbor cells. It can be in x direction or y direction, that doesn't matter, but it should have only one wall, I mean not wall, one side that is not wall but it is shared with the neighbor cell. If that is the case, we will have non-zero coefficient. So one non-zero coefficient from this cell and one non-zero coefficient from the neighbor cell. So we will have two non-zero coefficients. So in that case, we will go back and look at the question. So here, how many cells have one only one side that it is sharing with the neighboring cells? That is, that particular cell should have only one side that it is sharing with the neighbor cells, and rest all sides should be wall. So if we look at it, we can able to see the first, where is my cursor? This particular cell has one non-zero, one non-wall condition, and again this particular cell will has one non-wall conditions. Rest all, if you look at it, we have only this has one boundary condition, one boundary condition. Rest two surfaces are exposed to the neighboring cells. Similarly, if we take a look at it here also, two sides are exposed to the neighbor cells. So those things will not happen. So in this case, we have only one non-wall boundary condition that it is sharing with the neighboring cells, that happens with the top and the right corner points. Top and the this particular top and the right corner. Okay, so we have two. Therefore option B is the right answer. Option B is the right answer. 2. The number of rows exactly having two non-zero coefficients in the coefficient matrix. So it is actually, for each of the cell we have one equation, and we have the 10 cells, therefore 10 equations and 10 unknowns, and in each of the cell the number of coefficients will be considered, and if it is inside cell we will have pi for a square box, and depending on that, if there is only two non-zero coefficients, how many number of rows will have two non-zero coefficients? So number of rows is indirectly number of cells. So number of cells has two non-zero coefficients. It happens when that cell has cell is sharing only one wall with the neighbors. Rest all is wall boundary condition. So that is happening with the top and the right corner cell. So we have two two rows having exactly two non-zero coefficients in the coefficient matrix. So I hope it is clear. Option B is the right answer. Now we will go to question 8. In question 8, it is asked that if the algebraic equation resulting from the discretization of the governing equation on the grid in figure 3 are arranged in the form of a matrix equation, then the non-zero coefficients in the coefficient matrix will dash. I repeat, if the algebraic equations resulting from the discretization of the governing equation on the grid in figure 3 are arranged in the form of a matrix equation, then the non-zero coefficients in the coefficient matrix will dash. Option A, not have a diagonal structure. Option B, have a tridiagonal structure with 3 adjacent diagonals including the main diagonal. Option C, have a pentadiagonal structure with 5 adjacent diagonals including the main diagonal. Option D, have a pentadiagonal structure with 0 diagonals in between some of the non-zero diagonals. So, now we are going to questions that is dealing with figure 3. In figure 3, if the algebraic equations resulting from the discretization of the governing equations are arranged in the form of a matrix equation, what about the non-zero coefficients in the coefficient matrix will? Will they have a diagonal structure or will they not? And if they have diagonal structure, will it be a tridiagonal or a pentadiagonal? That is the question. So now in figure 3, actually if we go back, it has 16 cells. Oh. Not this, not this. I mean, it looks similar to this, but yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is figure 3 and we have 16 cells actually. And this is starred cell and this is colored cell. And if questions comes, I'm just explaining for you guys to remember it that time. So now we have 16 equations, and in these 16 equations we will have 16 unknowns. That is one thing. But apart from that, there are few equations which will have 5 non-zero coefficients. I mean, it won't be 5, but it will be 4. Or 5 or maximum it can be 5 or 4, and few it will be like which question were we? Yeah, few it will be like 2 non-zero coefficients and few in between 3, like that. So it won't have the diagonal structure. That is the answer actually. If you write and see also, you will be able to see that you won't be having a diagonal structure. Option A, not have a diagonal structure, is the answer therefore. Option A, not have a diagonal structure. Why? Because triangular cells cannot be named in a sequence I and J, and therefore no lexicographic ordering of the cells. So no possibility of diagonal structure of the coefficient matrix as well. So like we cannot name it in the ordering I and J, and therefore like we cannot put it in that order I minus 1 comma j, I plus 1 comma j. Those things will be like, it is not possible. So it is not possible to have the diagonal structure for the coefficient matrix. So option A, not have a diagonal structure, is the right answer. If the algebraic equation resulting from the discretization of the governing equation on grid in figure 3 are arranged in the form of a matrix equation, then the non-zero coefficient in the coefficient matrix will not have a diagonal structure. Option A is the right answer. Now we will go to question 9. In question 9, for the grid shown in figure 3, if the algebraic equations resulting from the discretization of the governing equation are shown in the form of a matrix equation, do you expect that diagonal dominance condition will be satisfied? So the question is about again figure 3, but here it is asked if the algebraic equation We are getting algebraic equation from the discretization of the governing equations, and it is arranged in the form of a matrix equations, and it is asked that will we expect it to follow diagonal dominance condition. Option A, diagonal dominant condition is irrelevant for unstructured grids. Option B, we cannot say a priori about the diagonal dominance condition. It will depend on parameters of the problem like size of the properties, size, properties of fluid, etc. Option C, exit, sorry. S, the equations can be ordered in such a way that the diagonal dominance condition will be satisfied. Option D, no, the diagonal dominance conditions cannot be satisfied no matter how the equations are ordered. So to put it simply, the question is about arrangement of the equations. After we are discretizing the equations, we will be getting the algebraic equations. So that equations we will be arranging it in a certain form, and we get the solution to those equations. And the solution can be uh, obtained from the numerical methods like Gauss-Seidel, Gauss-Seidel, sorry, um, whatever methods. And so we expect it to for have a diagonal dominance condition. So it can be arranged in such a way that it follows diagonal dominance condition is the right answer. So therefore option C, yes, the equations can be ordered in such a way that the diagonal dominance condition will be satisfied is the right answer. Option C is the right answer. Now we will go to question 10. Options answer is option C, as the equations can be ordered in such a way that the diagonal dominance condition will be satisfied. Since RHS of the governing equation is constant, LHS is of the divergence form. Option C is correct. So yeah, now it is about question 3. If the shaded triangle in figure 3 is a right angle isosceles triangle, then the direction cosines of the horizontal side are dash. Actually, I have given you a hint in the figure itself. This particular arrow is put by me. It is not in the question. So, if the shaded triangle in figure 3, this is figure 3 and this is the shaded triangle. It is a right angle isosceles triangle. So, as we can see, it is a right angle triangle and isosceles triangle as well. So, direction cosines nx and ny of the horizontal side are dash. So, it is horizontal side and it is a vertical side. So, horizontal side direction cosine is dash. Okay, I'll give the options first. Option A, it is 1 comma 0. Option B, it is 0 comma 1. Option C, it is minus 1 comma 0. Option D, it is 0 comma minus 1. If the shaded triangle in figure 3 is the right angle isosceles triangle, then the direction cosine of the horizontal side are dash. So the next question is actually depending on this particular question. It's similar to this question only. Answer to this question will be like help you in understanding that as well. So if you, it is a basic question. So direction cosine of the horizontal side of the right angle isosceles triangle is dash. So that is the question, and I have marked the direction cosine angle as well. So it would be easy for you to say of the horizontal side. So it is dash. So did anyone give answer? It is in the downward direction, right? So it is not 1, but it is -1 actually. It is almost correct, but since it is in the downward direction, it is option D is the right answer, where it is minus y, minus direction. So 0 comma -1. It is outward normal to that particular cell. That is the outward normal to the particular cell is the definition we have given in question 5 or somewhere we seen the definition, right? Yeah, direction cosines outward normal for each side. So that particular cell has outward normal in the negative y direction. If it is in the positive y direction, it would be 1. So it is not right. I mean 1 in the sense it will be like pointing inward. So the correct direction is negative y direction. So it is -1. 0 comma -1 is the answer. Oh. Yeah, 0 comma -1, that is option D is the right answer. Now we will go to question 11, question 10. Now components of the outward normal to the horizontal side in the right angled triangle are nx comma ny equal to cos of -90 and sine of -90, which is 0 comma -1. So that is option D is the right answer, 0 comma -1. So now we will go to question 11. If the starred triangle in figure 3 is the right angled isosceles triangle with vertical side of length A and horizontal side of length B, then the direction cosines nx and ny of the diagonal side are dash. The starred triangle in figure 3 is a right angle isosceles triangle with vertical side length A and horizontal side length B, then the direction of cosines of the diagonal side are dash. So I'll give the options. Option A, it is A by square root of A square plus B square, comma B by square root of A square by plus B square. Option B, it is B by square root of A square plus B square, comma A by square root of A square by A square plus B square. And option C, it is minus B by square root of A square plus B square and A by square root of A square plus B square. It is actually and option C, it is minus B by square root of A square plus B square, comma A by square root of A square plus B square. Option D, it is minus A by square root of A square plus B square, comma B by square root of A square plus B square. So just I'll give you a minute. If you can solve, you give me the answer. Otherwise, we'll solve it in a minute. B is the answer. the answer actually. Um, we'll see how actually. Hypotenuse. Okay. Hypotenuse of the starred cell is a square plus b square, because what it was mentioned, one horizontal side is a and sorry, horizontal side is length b and vertical side is length a. So hypotenuse is square root of a square by a square plus b square. So the direction for normal in the diagonal side is nx comma ny is equal to cos theta into comma sin theta. So cos theta is nothing but horizontal by hypotenuse, and sine is vertical by hypotenuse. So it is b by square root of a square plus b square plus a by square root of a square plus b square. So in other words, how we can say this is that, so it is a b c and we have a and b. So this is the normal direction it will point out. So if we resolve it into the direction cosines, the outward normal is in this direction. So we are resolving it in the direction cosines nx and ny. So AB is A, yeah, AB is A and BC is B, and AC, that is the hypotenuse, is square root of A square plus B square, and NX is nothing but cos 45. So this NX will give cos 45, that is B by hypotenuse. So B by hypotenuse will give nx, and similarly ny is a by for this side it is a by square root of a square plus b square. So it here it is for direction cosine in the x direction is b divided by hypotenuse side, and similarly in the y direction it is a divided by hypotenuse side. So a by square root of a square plus b square in the y, and b it is in the x it is b by square root of a square plus b square. So that is what we have given here as well. So cos theta it is horizontal by hypotenuse, and sin theta it is vertical by hypotenuse, and it is b by square root of a square plus b square, and comma a by square root of a square plus b square. Okay, that our next slide is more clear than this. What it is clear, I hope. That is the answer. Now we will go to next question. Same thing explained in different manner. That's it. But cosines we are just resolving. This is the outward normal. We are asked to find the direction cosines for this diagonal side. So I'll read the question once again. If the starred triangle in figure 3 is a right angle isosceles triangle with the vertical side of length A and horizontal side of length B, direction cosines of the diagonal side are dash. So the diagonal side length is first of all square root of a square plus b square, and the direction cosines we are taking x is like horizontal side b and b by hypotenuse, and vertical side it is a, so a by hypotenuse. So that's it. It is simple manner if we explain, that's it. So I'll go to next question. In deriving the set of algebraic equations for the grid shown in figure 3, boundary conditions are used for how many cells? In deriving the algebraic equations for the grid shown in figure 3, so this is the figure 3. Boundary conditions we are using in how many cells? So that is a question. So first option A, it is 9. Option B, it is 7. Option D, option A, it is 9. Option B, it is 7. Option C, it is 4. Option D, it is 3. So I'll read the question again. In deriving the set of algebraic equations for the grid shown in figure 3, boundary conditions are used for how many cells? So we are using boundary conditions in all those cells which is having boundaries as one layer, right? So here if we account it, we should see which are all the cells that has one side as boundary. So this is one cell, second cell, third cell, fourth cell, fifth cell, sixth cell, seventh cell, eighth cell, ninth cell. So we have 9 cells which are using the boundary conditions. So here when we are deriving the set of algebraic equations for the grid shown in figure 3, boundary conditions are used for how many cells? We are using the boundary conditions in those cells in which cell it shares one side with the boundary. One side with the boundary. At least one side, if it is sharing with the boundary, we are counting that cell. So here it is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is 9. Option A, 9 is the right answer. Option A, 9 is the right answer. Now we'll go to the next question. Total number of cells that have at least one side as wall is 9. In the next question, comparing the finite difference method and finite volume method for fluid flow problems, which of the statements is true? 1. Both methods would give the same result for fine grids. 2. For simple geometries, FD is preferable. 3. FD is preferable for complex geometries. Option A, 1 only. Option B, 2 only. Option 3, 1 and 2. Option D, 1 and 3. So, what is the question? In the question, it is a comparison between finite difference approach and finite volume approach. So, there are 3 statements given. We'll read over the statements and analyze which of them are true. Both the methods would give same results for fine grids. This is true because it is mentioned that in both of the methods, that is finite difference method and finite volume method, will give the same results when we are using very fine grids. Very fine grids results won't vary much between the finite difference approach and finite volume approach. You will read much about this in the later classes. But in general, to say finite difference and finite volume approach will give the same results when the grid size is very fine. So this is true. For simple geometries, FD is preferable. Again, this is true. FD is preferable for complex geometries. This is false. Because in complex geometries, we would not be able to use FD directly because it would be kind of complex to use FD method for the complex geometries. Rather, finite volume approach would suit better. So answer is 1 and 2 are right. So which is given in the option C. Option C is the right answer. Option C, 1 and 2 is right. So the finite difference approach is preferable for irregular geometries. Reasons will become apparently later, but primarily due to the ease of grid generation and refinement, as well as being able to work with governing equations in the physical domain. Like finite difference method, it is easier to generate grid when compared to the finite volume approach. That is why we are one small mistake happened here. Preferable for irregular geometries. I mean, it is not actually. Yeah. For simple geometries, FD is preferable. So this question I'll check again and let you know the answer in the next class properly. So coming to the okay. Okay, I'll confirm the answer to question 13 in the next slide. I mean next class. But for now, yeah, for now we'll go to last question for today's session. For a triangle having edges AB, BC and CA with the definition of vector XPQ as XPQ is equal to XQ minus XP equal to XQ minus XP into I vector plus YQ minus YP into J, the area of triangle is given by dash. Option A XAB into XBC, option B half into XAB into XBC, and option B half XAB comma XBC, and last one it is half into XAB into XBC plus XBC into XCA plus XCA into XAB. So here it is a triangle and whose edges are AB, BC, CA, and with the definitions as XPQ and XPQ as XQ minus XP. So it is rightly given. So it is answer is actually option C is the right answer. Sorry, option B is the right answer. Okay. Option B is the right answer. It is not A, it is B. Cross product of A, B and BC will give the uh, parallelogram, and dividing by 2 will give the area of the triangle. Half of it makes the area of the triangle. So answer is half into XAB cross XBC. So that is it for today's class. If you have any doubts, you can ask now. Or we'll meet next week at the same session. I think I went a little over time. But yeah, if there is any doubts, let me know. Yeah, then thank you for today's sessions and thank you for answering today's sessions as well. So, if there is any doubt, we can close the session. I am stopping the recording as well.